Let's start our class. In today's class, we will study the numerical aperture and that what it is that why it is important, and through which quantity it is denoted and how it is calculated. In the end of the lecture, we will do some numerical problem. So, why we study the numerical aperture and what is the numerical aperture? So we find the numerical aperture of the light collecting system in fiber optics communication. In fiber optics communication, the uh, in fiber optics communication, it is represented by Na. Na means the numerical aperture.
Warna biru.
It is represented by Na. We find the numerical aperture of the light collecting system in fiber optics communication, and it is represented by Na. There are two lighting collecting systems in fiber optics communication. If we want to communicate through optical fiber, so there are two types of collecting system. What is mean by collecting? So the system which collect the light. So when in transmitter, when you want to transmit the data, so this is the source which radiate the light, and this is the optical fiber. So we will optical fiber, we will focus the light of this source in optical fiber. So fiber that collects the light from the source. And how we will collect totally the light in this? So we have used in previous class the spherical lens, that by using the spherical lens, all the light of the radiated cone into the accepted cone, and this accepted cone is accepted by optical fiber, and then it will be travel in optical fiber. But the end of the transmission, this is the transmitter and this is the channel. Now we want to collect the light from the channel, mean optical fiber, to receiver. So the receiver that collect the light from the fiber. So this is the receiver, and uh, they will collect the light from the optical fiber. But you know that this is collimated beam of light, and we will focus this on a single point. So how we will do this? So we shall find out the numerical aperture of the fiber as well as receiver. So we will use the numerical aperture, and we will calculate the numerical aperture for photodetector, as the photodetector is behave like receiver, and it will receive the collimated beam of light from the optical fiber. So we assume that the photodetector is the form of circle that with diameter d. So consider we use the receiver, which is photodetector, and this photodetector is in the form of circle, and the diameter of the circle is d. We want to focus the collimated beam of light to the center of the photodetector. You see here, this is the photodetector and this is the center. So we want to concentrate to collect all these collimated beam of light at the center of a photodetector. So for this purpose, we will use the spherical lens. And you know that when the when the collimated beam applied fall on the spherical lens. So when the collimated beam applied fall on the spherical lens, so this collimated beam applied will focus all the light in a single point. And why they convert this? When we place the the photodetector at focal point, so it is the property of the spherical lens that when the lights fall on the surface of the spherical lens, which is parallel to the principal axis, so they will focus them in a point, and this point is called focal point. And the distance between this point and the surface of the spherical lens is called focal length. It means that we want to focus the collimated beam applied to center of photodetector. We place this circular detector at the focal point of a spherical lens. The spherical lens focus all the rays of collimated beam applied to the center of a receiver. So this is the receiver and this is its center. So the collimated beam of light will focus all the rays in focus all the ray to the center of the focal to the center of the photodetector. And you see that this photodetector is just a line. But why this is a line? So it is a spherical surface. But when you see the circle from the side, so it will see like a line. For example, this is a spherical lens and this is a spherical photodetector. So when we fall this collimated beam of light, so it will focus all these light at the center. But when we see here, so you will when you see from the side, so you will see the spherical lens is just a line and this is also just a line. So it will seem like this is the collimated beam of light, and when this collimated beam of light fall on the spherical surface, they will concentrate it a center. This is the center. So if the collimated beam of light makes an angle, sometimes this collimated beam of light make an angle with the of theta with respect to an axis. For example, you see here, this is the axis of the spherical lens, and this is the center ray. This is the center ray, and you know that the central ray will undeviated. So this circle ray is undeviated, and this ray is parallel to the center ray, and this is the property of the spherical lens that when the when the light fall parallel to the center ray, when we the light falls parallel to the center ray, it will focus at the it will cross the central ray, and as this is parallel to the central ray, so after transmission from the spherical lens, it will cross the central ray at same point. It means that in previous figure all the rays were concentrated at the center. Now they are not in the center. They are some distance away from the center, as the ray make angle theta with x-axis. So what is the effect of this theta? When this theta become large, so maybe it will not uh, concentrated at the surface of photodetector. For example, if you see here, if we increase this theta, so when we increase the theta, so the lights will be concentrated at that point, and this point is not lie in the photodetector, so we'll unable to detect our light, and it means that our receiver will not receive any signal. So it means that this angle is very important in optical communication. So if the collimated beam applied make angle theta with respect to axis of the lens, then the beam is focused at the lower edge of the photodetector. You see that this is the lower edge of photodetector, and theta is equal to maximum acceptance angle of receiver. This theta will be not exceed a specific limit, and this limit is called maximum acceptance angle of receiver. When the light is increased from the maximum acceptance angle, so the light will be concentrated at the point which will be not lie in the photodetector. In this case, we will not receive any signal. So this is the maximum acceptance angle of the receiver. If we increase the angle beyond this value, the receiver will not receive light ray as shown in the figure. So we consider the right angle triangle on the right side of the spherical lens. Here you that this is the angle theta, which is the its value is less than the theta maximum, where theta maximum is the maximum acceptance angle. And let's consider this triangle here. What is the value of this? This value is equal to f. And what is this? The distance from that point to this point. So you know that this is the whole diameter of the spherical lens, and this is the center. So the distance from the center to the edge is d by 2. So the distance from this point to this point is d by 2, and the distance from this point to this point is f, which is the focal length. So this is the focal length, and this is the d by 2. So tangent theta is equal to d by 2 f. So tangent theta is equal to d by 2f. And you know that the theta is equal to tangent inverse theta is equal to tangent inverse of d divided by 2f. This is the theta, and this theta, if here this theta must be is equal to theta m, as we consider that distance from we consider that the distance from the center to the edge is d by 2 here. So it means that this theta is the maximum acceptance angle. So up to now you have studied that what is the maximum acceptance angle and why it is necessary. The maximum acceptance angle is that angle that beyond of that value we are unable to receive any signal, but but when this value is less than theta, if this angle is less than the specific value, so we will receive a signal. So here we consider the maximum value of the theta beyond which we are unable to receive the signal. So it means that this theta is the maximum acceptance angle, and this is the triangle which we have take here. This is the triangle, and we have redraw this triangle here. So this is the theta, and this is the f, and this is the d by 2. But here we have connect there is specific value, and we have redraw the triangle here. By using this triangle,
सर जी आवाज मो खराब दे
by using this triangle, अभी clear है?
या सर देना मखी खबर मन सर कोई नो आवाज खराब
ठीक है। तो पहले मैंने ये कहा कि ये जो मेरे साथ ट्रायंगल है, ये जो ट्रायंगल मैंने इधर ड्रा किया है, ये वाली ट्रायंगल यहाँ से लेकर यहाँ तक, दिस ट्रायंगल। सो इस ट्रायंगल को मैंने इधर जस्ट रीड्रा कर दिया। वी द डिस्टेंस फ्रॉम दिस पॉइंट and to this point is f, and the distance from this point to this point is d by 2. So here we have redraw the triangle. This is the theta, this is the f, and this is d by 2. So the tangent theta is d by 2f, and theta is equal to tangent inverse into d by 2f. Uh, so theta is tangent inverse d divided by 2f. This is the maximum acceptance angle. That's how you will calculate the maximum acceptance angle of the photodetector. So you, if someone asks that the focal length of the spherical lens, the focal length of the spherical lens is f, and the diameter of the photodetector is d, calculate the maximum acceptance angle. So you can calculate using this equation. But now we want to study the numerical aperture. As the numerical aperture depend on this theta, so that is why we firstly define this theta. So the numerical aperture is equal to n naught sine theta, where n naught is the
सर जी
representation.
تاسو नेटवर्क सही
سر आवाज یو خراب راځي سر نه راځي
So Na ما ته خو هلکانو دلته نه ښایي چې ستا نیټورک کمزوری دی. په مخکې ساعت کې ښولی و.
ټولو ته خراب دي سر زما
सर تاسو आवाज خراب دي
راځي
ها چې ته لږ دغه شه ځان ته لږ remove. Here you see that the Na is equal to n naught sine theta, where n naught is the refractive index of the medium and theta is the maximum acceptance angle. So this equation is show the numerical aperture. That numerical aperture is equal to n naught time of the sine of the maximum acceptance angle. You can write this: the numerical aperture is not time of the sine of maximum acceptance angle theta. And it is and its equation is Na n naught. But in the case of ear, so the n naught value will be 1. So it means that n is equal to sine theta. N is equal to sine theta. Let's consider the any simple example here, that if the alpha naught is the 40 degree. What is mean by alpha naught? The object angle is 40 degree and the image angle is 10 degree. Calculate the m. आप a magnification calculate करें, ठीक है. And so you know that m is equal to alpha naught divided by alpha I. So this is 40 divided by 10, so this is equal to 4. And you know that m is equal to 1 divided by d naught. M is equal to 1 divided by d naught by f minus 1. And if we consider, if we take reciprocal of both, so d naught by f minus 1 is equal to 1 over m. So d naught by f minus 1 is equal to 1 over m. So d naught by f is equal to 1 plus 1 over m. If we write the values 1 plus 1, m की value क्या है 4. It means d naught divided by f is equal to 4 by 5 by 4. It means that d naught is equal to 1.25. It means that 1 plus 1 over 4 is equal to d naught divided by f is equal to 5 by 4. This is equal to d naught is equal to 1 point. This is not 0, this is point. 1.25 f. So it means that numerical question में हमसे ये पूछा था कि find the m and d naught. So the value of the m is 4, but the value of the d naught is 1.25 of f. If the f is given, so we can calculate the d naught. So if the f is 10 centimeter, it means that the d naught is 12.5 centimeter. And if someone say that calculate the di, so you can calculate by formula that 1 over f is equal to 1 over d naught less 1 over di. Here we know the f and d naught, so we can calculate the di. So simple question. This was very simple question. That when the object angle is given and the image angle is given, so you can calculate the m and you can calculate the d naught and di if the frequency of the lens is given. So here you know that m is equal to di by d naught also from this equation. So d is equal to m d naught. So 4 into 12.5, it means this is the 50 centimeter. If we place the optical fiber at 50 centimeter, then it will get, then we will get these rays. So consider the second example. The photo detector diameter is d, which is 1 centimeter, and the focal length of the spherical lens is 1 over 2 centimeter. So find the maximum acceptance angle theta and calculate the numerical aperture Na. So you know that the tangent theta is d divided by 12. So 1 divided by 2 into this, it means theta is equal to 45 degree. Tangent theta is equal to 1. So theta inverse of 1 is equal to 45 degree. And what is numerical aperture? So n is equal to n naught sine theta, as this is ear. So in the case of ear, you will write the n naught is equal to 1 and sine 45. So this is 0.707. This is the numerical aperture of the uh, photodetector.
په دې numerical aperture باندې پوه نه شو سر numerical aperture څه ته وي؟